Okay class, let's begin our unit number 2. So, orientation. The amorphous and crystalline states of polymer has been thoroughly studied. We all know what is amorphous and what is crystalline polymer. Crystalline polymer is densely packed, amorphous polymer is loosely packed, you know. So therefore they are quite well understood, but there is an oriented state intermediate between the two in regularity, but quite different in its morphological phenomena. May be equally important, particularly in practical applications such as fiber films and probably also foams. But it has been much less studied and is much less understood. Let us spark, this is partly because sufficient analytical techniques have not yet been developed for such studies. So remember, there are two types of polymer, amorphous and crystalline, and in between them there is oriented polymers. Okay? And partly because of a popular confusion between crystallinity and orientation. So there is a confusion also between crystallinity and orientation. These phenomena should be clearly distinguished from each other, and it may be hoped that present and future development of more appropriate analytical technique will eventually lead to clearer understanding and utilization of the oriented state. For a review of what has already been accomplished, it is convenient to consider first the processing techniques that led to orientation, and then the effects of orientation upon properties and application. Processing and orientation. When a molten polymer is cooled from the liquid to the solid state, the molecules, whether amorphous or crystalline, lies in the random orientation and in the total sample. Random orientation in the total sample. Under directional mechanical stress, the axis of the polymer segments of crystallites tends to rotate in a position parallel to the direction of stress. By which this is the mechanism by which orientation occurs. So just imagine you have a polymer which is in the liquid form and you cool it into a solid state. So what will happen? All the crystalline all the molecules, whether they are amorphous or crystalline, they will simply lie in the random orientation, means any zigzag manner. But if you provide a directional mechanical stress, suppose you provide it in the direction of the x-axis, then all the polymer segments or the crystallites tend to be in the parallel to that direction stress. So that all the molecules will be now directed towards the x-axis. This is the mechanism by which orientation occurs. Intermolecular order is the geometrical relationship between adjacent polymer molecules and their arrangement in the total mass of the polymeric material. At present, polymer science recognizes three different states of intermolecular order. So in polymer science, there are three states of intermolecular order. They are, as you know, crystalline, amorphous, and oriented. When polymer molecules are arranged in completely random intertwined coils, this completely unordered structure is known as amorphous state. Like you know, in amorphous there is no orderly arrangement; it is completely unordered. When the polymer molecules are so neatly arranged that each of their atoms fall in precise position in a tight packed repeating regular structure. This highly ordered structure is described as crystalline state. When polymer molecules are stretched into a rather linear conformation and are fairly parallel to each other in the mass of this partially ordered structure is described as oriented state. In practice, some polymers are completely amorphous, others are partly amorphous and partly crystalline. Partially ordered structure is described as oriented state. Okay. Highly ordered structure is defined as crystalline state and unordered structure is defined as amorphous state. In practice, some polymers are completely amorphous, others are partly amorphous and partly crystalline, others are partly amorphous and partly oriented, and still others are partly amorphous, partly crystalline, partly oriented. At present, it seems unlikely that polymers can be obtained in completely crystalline or completely oriented state. Each of these three states has very distinctive effects upon polymer properties, and polymers which contain combinations of these states show their combined effects. So 100% crystalline polymer does not exist. It may have some parts of oriented and some parts of amorphous states also. So let's see amorphous state. The preceding discussion of molecular flexibility described the random coiling and behavior of individual polymer molecules. Implicit in their entire discussion, however, was the fact that these random coil molecules are all intertwined and intertangled with each other, and that their behavior in response to any type of stress is largely a measure of the ease or reluctance with which they can disentangle to relieve that stress. Typically, commercial polymers include polystyrene, polyvinyl acetate, polymethyl methacrylate, and most random copolymers and elastomers. Thus, discussion of flexibility of the individual polymer molecules has already implicitly described the amorphous state in considerable detail. And no further discussion is necessary at this point. Rather, what is now important is to consider the ways in which the crystalline and oriented state differ from the random amorphous state in their structure and their effects upon polymer properties. Crystallinity. The nature of crystallinity in polymers, conventional crystallinity in monomeric materials. In a single pure monomeric species at low temperature, the individual molecules are packed in a neat orderly crystalline arrangement. Of high density, sharp melting points, and low solubility. The stability of such a high the ordered structure at low temperature and energy level is demonstrated by the heat of fusion or enthalpy delta H, which is liberated during the formation of the crystal, and which must be supplied in order to melt and disperse the molecules out of the crystal. At high temperatures, the energy levels, on the other hand, vibration and Brownian motions of the molecules tend to drive them apart, destroying the crystals and dispersing them into highly random and disordered state containing many degrees of freedom, as represented by the entropy delta S. The balance between these two factors determines the melting point of each particular material. So the melting point Tm is equals to ratio of delta H upon delta S. Now mechanical property. So delta H, enthalpy is the amount of heat needed to break the crystal into amorphous or unordered state, and entropy is the disorderliness of the system. So its ratio gives you the melting point. That's all regarding crystalline polymers. So I hope you just write down some examples of these three types of polymers: oriented polymers, then amorphous polymers, then crystalline polymers. Mechanical properties. The effects of mechanical the effects of molecular weight upon mechanical properties and upon physical properties in general are among the most frequently studied of the many structure property relationships, both theoretical and applied. In most fundamental and general approach to this relationship, the thermal energy of atoms and molecules keep them in constant vibratory motion. If the entire molecule is very small and the attractive forces between the molecules are not too great, these molecules move freely throughout the space in the form of gas. If the molecules are somewhat larger and the attractive forces between them are somewhat greater, they still move fairly freely in the form of liquid. And the size of molecules become greater, they exist in solid form. So when the mechanical stress is applied to such a low molecular weight solid, the molecules side over each other and separate from each other. The solid has very little mechanical strength and is of very little structural value. With continuing increase in molecular weight, the molecules become entangled and the attractive forces between them become greater and the mechanical strength begins to appear. Ultimately, the sum of the entanglement and intermolecular attractive forces become greater than the strength of the individual covalent bonds in the backbone of the polymeric chain. When mechanical stress is applied to such a high molecular weight system, it may be easier to break primary covalent bonds in polymer backbone than to separate one polymer molecule from another. Beyond this point, further increase in the molecular weight produces no further increase in the mechanical strength. Mechanical properties may best be divided into three types of classes: reversible rigidity, flexibility, or modulus, which measures the stiffness of the polymeric system; mechanical failure by yielding or breaking at low conventional ultimate strength and elongation, or high impact rates or test. Multiple cyclic steps, complex mechanical properties involving combination of these simpler processes. These classes are now considered in detail. So you can see here molecular weight is increasing on the x-axis: 500, 2500, 5000, 10,000, like that, and percentage crystallinity. So it's just direct percentage crystallinity is directly proportional to molecular weight, because initially it was liquids, greases. Then as the molecular weight increased, it became soft waxes, then brittle waxes, then tough waxes, then hard plastics, then soft plastics. Thermal properties. The huh? Just thermal properties. The effects of molecular weight on thermal properties are most evident in three areas: thermal mechanical properties, thermodynamic properties, thermal stability. So, thermal mechanical properties. The effect of molecular weight on thermal mechanical properties is best understood by examining its effects on the relationship between modulus and temperature. In a linear amorphous polymer at low temperature, the atoms in the polymer molecule have little thermal energy of vibration, and heavily intertwined polymer molecules are quite immobile and unable to move past each other. even under mechanical stress. In this region, the polymer is rigid and glassy. As the temperature increases, the atoms and groups in the polymer molecule acquire an increasing amount of thermal energy, causing them to vibrate and move about. The higher the temperature, the greater the thermal motion, and larger the sequences of atoms in the polymer chain that become mobile in this way. At some critical temperature called the gas transition temperature (TG), or more properly in some critical narrow temperature range, this mobility begins to involve polymer chain segments large enough to permit substantial motion within the polymer mass. Beyond this point, when mechanical stress is applied, motion of large segment of polymer chain segment is sufficient to permit the motion of the entire polymer mass. In this transition region, the polymer mechanical behavior is a free, flexible, or leathery. At still higher temperature, the mobility of large polymer segment is sufficiently high so that the polymer can yield easily under mechanical stress, and its total behavior is flexible and rubbery. So if you increase the temperature, then initially the behavior of the polymer will be stiffly flexible or leathery, but at still higher temperature it will be flexible and rubbery. This flexible rubbery plateau is the temperature range in which the polymer yields easily to mechanical stress and recovers readily when the stress is released. At still higher temperature, the thermal energy and the mobility of the atoms and large segments of the polymer molecule become so high that when the mechanical stress is applied, the entire polymer molecule tends to disentangle and flow past each other. This is the second transition region polymer behavior is described as rubbery flow, meaning that it will be mildly elastic under low mechanical stress but permit permanent deformation and flow under higher mechanical stress. Finally, at still higher temperatures, the thermal energy and mobility of the polymer molecule becomes so high that they flow easily and permanently under mechanical stress and are desirably describable as truly liquid in character. The effects of molecular weight and thermal mechanical properties are best understood by examining their effects on each of these regions in turn. So you see effects of temperature upon modulus oxygen amorphous polymer. So like I said, when you increase the temperature, first it is a glassy state, then glass transition, then leathery region and rubbery plateau. Here it will be deformed and got back to its original position because it is elastic, and then finally permanent deformation, rubbery flow and liquid flow. Thermodynamic properties. Fundamental thermodynamic properties of polymers have not yet been thoroughly explored, yet there has been a start toward the understanding of the relationship between the molecular weight and two fundamental thermodynamic properties: thermal conductivity and coefficient of thermal expansion. Thermal conductivity of polymer is generally much lower than that of the most other materials, and in fact, many uses of polymer are based on their efficiency as thermal insulators. Yeah, because plastic cannot carry current, so they have very low thermal conductivity. Therefore, they are used as thermal insulators. Some of the deficiencies of polymer also result from their inability to conduct heat. So it has positive as well as negative effects. Thermal conductivity does not vary greatly with conditions. It is somewhat dependent upon molecular weight because the atomic vibrations of thermal energy are transmitted more directly along the covalent bond in the polymer molecule than across the weakly bonded regions between the polymer molecules. At molecular weight up to 1 lakh, thermal conductivity is proportional to the square root of weight average molecular weight. At molecular weights above 1 lakh, thermal conductivity becomes less sensitive to molecular weight and considerably more constant. So, in the range of 1 lakh, thermal conductivity is proportional to the square root of the weight average molecular weight. And then it is less sensitive to it after that molecular weight. And thermal conductivity, because of thermal insulation, most of the handles of the cookers which we use in the kitchen are made of polymers because we cook food, the cooker becomes hot, but we have to carry it, so we need something to hold which won't have that much heat as the cooker has. So we use the plastic handles on the cooker to carry the food. So that's thermal conductivity, thermal insulation, and wires. Coefficient of thermal expansion. Polymers have a much higher coefficient of thermal expansion than do most other materials, particularly metals. And this is a serious problem in highly precise design of components. Coefficient of thermal expansion depends upon molecular weight, primarily because the end groups of the polymer molecule are more flexible and mobile and occupy a large free volume. Thus, it is not surprising that coefficient of thermal expansion is inversely related to number average molecular weight. For example, polystyrene in the rubbery state, alpha 1 equals to 5.46 into 10 to the power minus 4 plus 3.5 into 10 to the power minus 4 upon Pn. In gaseous state, alpha G is equals to 1.81 into 10 to the power minus 4 plus 2.76, where Pn is the number average degree of polymerization and alpha is given in centimeter cube. So naturally in gaseous state the number average molecular weight will be higher, so therefore the coefficient of thermal expansion is quite less in gaseous state because it is inversely proportional to the number average molecular weight, and in the rubbery state it is higher. Thermal stability. While most commercial polymers are reasonably stable at temperatures used with final products and up to normal processing temperature, they are generally less stable than metals and ceramics when heated to very high temperatures. Since thermal degradation, oxidation, and hydrolysis are characteristics of most important organic material at high temperature, it is not surprising that similar reactions should occur in organic polymers. Since there is a great need and demand for thermal stability in many of the potential new applications of polymer, however, thermal stability remains a critical concern to polymer scientists and has been the basis of many fundamental studies. So many practical studies, thermal stability appears to be directly related to molecular weight. This is due to the fact that while the polymer itself has a fairly stable structure, much of its instability of polymers arises from the different nature of end groups on this polymer molecule. For example, the initiator used in most addition polymerization reaction often leave initiator fragment attached to the end of the polymer molecule. The mere polymerization reactions terminate by disproportionation. The resulting unsaturated C-double-bond end group are point of instability in the finished polymer molecule. When vinyl polymerization reaction terminate by chain transfer with initiator, solvent, or purposeful chain transfer agent. These end groups are frequently less stable than the rest of the polymer molecule and form a point of thermal instability. In condensation polymers, the end groups are frequently polar reactive functional groups of much higher chemical reactivity than the rest of the polymer molecule. Thus, in most polymers, the end groups form points of particular reactivity and thermal instability. Consequently, it is not surprising that thermal stability is directly related to molecular weight. Conversely, when polymers are heated to the point at which further reactions occur, either during processing or during final use, these reactions may cause either degradation or lower molecular weight or cross-linking to higher, sometimes almost infinite molecular weight. Thus, in relationships between molecular weight and thermal stability, molecular weight may be cause and or effect. Now, electrical properties. While electrical properties are generally independent of molecular weight of the polymer itself, they are very strongly affected by the addition of monomeric liquid plasticizer to form a mobile low molecular weight fraction of the total composition. The mechanism of these effects on resistance dielectric properties is quite different, and they are best considered separately. So basically, molecular weight is not affect does not affect the electrical properties, but the addition of monomeric liquid plasticizers do affect the electrical properties. Resistance. Most polymers are excellent electrical insulator, we all know, and display high electrical resistance and very little conduction of an electrical current. The small conductivity which is observed in is probably due primarily to the electrolytic motion of the ionic impurities of the polymer. तो जितनी भी स्मॉल कंडक्टिविटी हो जाती है कभी कभी प्लास्टिक में बिकॉज ऑफ द इम्प्योरिटी. Thus, a decrease in electrical resistivity is generally the result of both ionic impurities and mobility. While ionic impurities may be difficult to determine, mobility is easily measured by mechanical and thermal properties and is particularly affected by the addition of plasticizers. Thus, conductance is directly related to plasticizer content. The resistivity of plasticized polyvinyl chloride decreases regularly with increasing plasticizer content. The relationship between mobility in general and electrical conduction is clearly evident in the twin effect of the plasticizer upon mechanical modulus and volume resistivity of the plasticized polyvinyl chloride, as shown in table 3-3. While these effects are quite large, the electrical resistivity of plasticized polyvinyl chloride is still high enough for wide use in electrical wires and cable insulation, largely because of its combination of processing flexibility, coloring, weather resistance, and low cost. So, effect of plasticizer content upon electrical resistivity of triacetyl phosphate polyvinyl chloride. Okay. So, what is happening here is you can see in this graph, this is triacetyl phosphate, and it is the resistivity. So, as the plasticizer content is increasing, the resistivity is decreasing. On the y-axis, there is resistivity, ohm centimeter. So first, plasticizer content was low, only 10% approximately. So the resistivity was quite high, but then it went on increasing. So the resistivity goes on decreasing. Same here, plasticizer content 50%, lock conductance fall everywhere the conductance is increasing with increasing amount of plasticizer. More the plasticizer, more the conductance. Resistivity goes on decreasing, more the plasticizer content, and conductance goes on increasing with more the plasticizer content. Optical properties. While it has been observed that optical properties do not generally depend on molecular weight, it seems reasonable to expect that in low molecular weight polymers, the different nature of the end groups or most polymer molecules would produce some changes in the absorption of refraction of light. Absorption and refraction of light. Low molecular weight polymers, the different nature of the end groups or most polymer molecules would produce some changes in absorption and refraction of light. It has already been explained how molecular weight and distribution affect processability of polyethylene into films form. This in turn affects the optical properties of the resulting film. Thus, low molecular weight favors high clarity and gloss. Nanomolecular weight distribution favors high clarity, while broad molecular weight distribution favors high gloss. Similar relationships undoubtedly apply to other polymers as well. You know what is gloss? Gloss is nothing but shining of the paper. Like if you read a newspaper, it doesn't have gloss, but if you read a magazine paper, then it will have gloss. Chemical properties. The molecular weight of the polymer molecule has a number of significant effects upon its chemical properties. So you can see here gloss is increasing and the melt index is increasing. Melt index means broad molecular weight distribution. So let us see the chemical body. The molecular weight of the polymer molecule has a number of significant effects upon its chemical properties. Why there is not universal agreement on these relationships, they are important enough to deserve careful note, and they are best divided into several groups of related properties: solubility, extraction, stress cracking, swelling, absorption, and permeability, reactivity, and aging. Solubility. In general, generally accepted that solubility of a polymer molecule is solvent is inverse to the molecular weight. One of the most striking and classic examples of Ostomyslensky's early pioneering studies of the relationship between molecular weight and solubility of polymer chloride. Such considerations are particularly important in the formulation of solution coatings such as paint and lacquers, where the solvent balance is often very critical. Compatibility of polymers with plasticizers may similarly be inverse to the molecular weight, which would affect the latitude available to formulators of plasticized polymers. So extraction. It follows then that in a polymer of broad molecular weight distribution, even though the majority of high molecular weight polymer is solvent resistant, the low molecular weight fraction provides a significant basis of solubility and extractability, which must be considered in practical applications. So majority of high molecular weight polymers are solvent resistant, Low molecular weight fractions may provide significant basis of solubility and extractability, which must be considered in practical application, particularly when the high molecular weight polymer is cross-linked during processing. The low molecular weight fraction is statistically least likely to cross-link and therefore remains a highly soluble and extractable fraction in the pharmacopoeia. As an extreme case, the addition plasticizers and other monomeric and low molecular weight ingredients to an otherwise solvent resistant polymer during compounding introduces a low molecular weight fraction of the high solubility and extractability, and thus lower the overall chemical resistance of the total composition. Stress cracking. Stress cracking appears to be a specialized case of the extractability of low molecular weight fractions in polymer, which probably explains why it is inversely related to the number average weight. This effect has been most thoroughly studied in polyethylene, but undoubtedly is of major importance in many other polymers as well. So, effect of molecular weight upon stress cracking resistance of low density polyethylene. Note that the increasing melt index indicates decreasing molecular weight. So, more the melt index, decreasing the molecular weight. Hours to failure, stress. So, you can see the stress is increasing here. And this is the melt index. So increasing the melt index indicates decreasing molecular weight. So here the melt index is high, means 20 melt index indicates decreasing molecular weight. So this has the least molecular weight. So even in a low stress as 4, the hours of failure is only 10 hours. Then the melt index is reduced, so the molecular weight is increased. So the hours of failure is increased, like that. Effects of chloroform extractable fractions upon stress crack life of low density polyethylene. So this is the chloroform extractable fraction. If it is 11.8%, stress cracking time in equipal at 50 degrees 4 hours. If it is further reduced, then the hours are also increased. Okay. Swelling, absorption, and permeability. There is less agreement on the effects of molecular weight on swelling, absorption, diffusion, and permeability through a polymer, while permeation by liquid and gases. It has also been reported that molecular weight has inverse effects on swelling, absorption, and permeability. So, in polyethylene, increasing molecular weight produces increased greaseproofness and slightly lower gas permeability. A more detailed examination, sorry, of absorption in glassy polymers suggests that when such a glassy polymer absorbs solvent, this results in plasticization, which lowers the glass transition temperature, increases mobility, and therefore produces even higher absorption. So just remember that swelling, absorption, and permeability is inversely proportional to molecular weight. Reactivity and aging. Reactivity, the N group of the polymer molecule is frequently the most reactive point in the entire molecule. Vinyl polymerization, which terminates by disproportionation, leaves C double bond C bond on the end of the polymer molecule and is still quite reactive. Vinyl polymerization, which terminates by transfer solvent, initiator monomer, or chain transfer agent, all attach reactive group to the end group of polymer molecule. Most condensation polymerization reactions leave few unreacted polymerizable group at the end of the polymer molecule, and this remain quite as reactive as any of those which has entered polymerization reactor. Thus, In most polymer systems, the end groups on the polymer molecule is the one most reactive position in the entire polymer molecule. Since the number of the end groups is exactly inverse to the number average molecular weight, it is to be expected that polymer reactivity would be inverse to molecular weight. So reactivity is also inverse to molecular weight. Okay, it has long been observed that the lower mobility of high molecular weight polymers makes them much less reactive to normal chemical reactions than similar functional groups would be in conventional low molecular weight monomeric structures. To this extent, increasing molecular weight would be expected to decrease reactivity. Increasing molecular weight would be expected to decrease reactivity quite rapidly, then taper off at higher molecular weights. Aging. Reactivity with oxygen, ozone, and moisture and ultraviolet light. Sensitization of such reactions all become important during long-term aging of polymers in use, particularly at high temperature or in outdoor, where the resistance to deterioration should be directly related to molecular weight of three distinct meters. Reactive end groups are inverse to the number of molecular weight. Reactivity of high molecular weight species of low mobility is much less for molecular weight species of higher mobility. Okay, degradation of very high molecular weight polymers during aging may still only degrade them to medium molecular weight polymers of almost equivalent properties, whereas degradation of medium molecular weight polymers during aging may degrade them to such small molecules that a significant loss in properties results. So these are the properties: degradation during aging on the y-axis, molecular weight. As the molecular weight increases, the degradation during aging. Very less, because it is going in this direction. So lesser the molecular weight, more the degradation. Effects of molecular weight upon degradation properties. Degradation of property during aging. Not only does molecular weight affect aging, but also affects molecular weight. But aging also affects molecular weight. So they both affect each other. Aging may either lower the molecular weight of polymer by cleavage, or may produce cross-linking up to infinite molecular weight. Thus, molecular weight and aging may be cause and effect, or effect. So this is all regarding the dependence of molecular weight of properties of polymers on molecular.